there's no doubt that this is a timely moment for discussing this topic. We have seen the unprecedented amount of data that we have available that have given rise to informatics science, bioinformatics, informatic astrophysics. Astrophysicists don't look anymore the sky with telescope, they look into databases that are created with radio telescopes that are accumulating data. And we know that in the present moment, that's complexity, Mexican complexity. Yes, in this moment, everybody surprised with the capabilities of these new models of artificial intelligence, the large language models. And we know that they are here in part. That's one of the dimensions, because the enormous amount of data that we have available. But in this context, I would like for you to focus on the potential, the potential scope of the future impact of artificial intelligence in the development of scientific knowledge. And being more precise, I would propose for you to take turns in giving your reaction to the question of what have been the principal contributions of computational science to complexity science. And we could start with you, Boris.
Does this work? Well, thank you very much, first of all, Chris, for inviting me to this panel. I'm happy, and it's an honor to be here. Thank you very much. Well, this is an interesting question. I think we cannot separate complexity sciences from computer science and data science and artificial intelligence. One comes with the other one. I mean, at the beginning, of course, we have complex problems. We have to model them, and we need computer model and mathematical model. And for that, it's been essential to have these things. No? We just heard Gemma's talk about the importance of complexity. So that's something we have to measure, no? How complex the problems are. So we come here again to the side of algorithm theory and computations, and whether problems are P or NP hard, etc., etc. But I think the great breakthrough in the last years, in the last 20 years, is definitely the rise of machine learning. Yeah, and this has come. It has become very important. Why? Because complexity problems are by definition complex, meaning that there are many variables involved in solving these problems. We humans are good at solving problems with few dimensions. It has to do with visual perception. We are very good at solving problems where you have 2 or 3 dimensions. But complex problems like climate, energy, agriculture, that kind of things have to do with lots of variables. It's a multidimensional problem. And these methods of machine learning are very good at analyzing correlating variables and to see which one of them are very good at. So data science, machine learning, and lately deep learning models have become crucial to solve these problems. And just to finish, there's something new, which is quantum computing, which is going to help solve optimization problems which are very difficult to solve in classic computer.
I would like you to answering this first, I think, not difficult question. to take in mind that the second question I would like you to focus is also what kind of virtuous relationship do we expect to emerge between the new artificial intelligence paradigms and science in general, and particularly in complexity science. But what if we follow with you, Carlos?
Thank you, Humberto. So before we had telescopes, we could only perceive planets as far as Saturn and just our moon. Later, with Galileo's telescope, he perceived 4 largest satellites of Jupiter. First galaxies outside our own were perceived about 100 years ago, the first exoplanets only in the 1990s. So, I mean, it is clear that if we don't have the proper tools to study natural phenomena, we will be limited. The same before microscopes, there were different theories about what caused disease, and actually it took 200 years for the germ theory to be accepted, 200 years after there were microscopes. And how will we prevent and cure disease if we don't know the causes? And in a similar way, Heinz Pagels in the 1980s wrote that computers were the telescopes for complexity, because before we simply didn't have the tools to consider interactions that characterize complex systems. It's not that people were not aware of the relevance of interactions, just, I mean, ecology is by definition complex, but if you are limited to blackboards or notebooks, maybe you can deal with 2 or 3 variables. And if you want to study 1,000 or 1,000,000 variables, you need computers. So it's not a coincidence that the scientific study of complex systems exploded with the availability of personal computers. Before, it was restricted to few institutions that had computers. And since the 1980s, it has become possible for everybody to study computers, and it has become more and more widespread. So let's say we can see computers as a tool for studying complexity, and without them, I mean, I don't know what we would be doing. And we see this, let's say, with the increase of not only computational power, but availability of data, algorithms, and all the things that we can do because of this technology.
Same question. Taking into account what Boris just said us, is that it's not only computational. Somehow computational science had to do with the very basic fact that we need to solve differential equations in the models of physics, engineering, and other fields. But also machine learning techniques have given us access to this huge amount of data that now are available. So please take this in account.
Yeah, I think that the most interesting thing that's happened over the last decade within machine learning and AI is the ability to solve hard translation problems at scale. So we're witnessing an unprecedented ability to remap data from one form into another, while preserving a lot of the superficial structure. And I think that this is a real boon potentially to science. The flip side, though, is the data-driven enterprise that's gone into it is one in which the focus on the typical is likely to squash the atypical. And a lot of things that are really interesting in complexity science are things that aren't necessarily the common occurrences. When I tell my students how to use an LLM well, I tell them, ask it what everybody would think, because that's what it's really good at responding to, and then it'll give it to you in a bullet point format, right? 1, 2, 3, 4, that factorized format that I cannot stand to read another news article if it's in that format. Anyway, with all of those translation capabilities, I think though there's something else that's kind of interesting, and that's science really progresses when you find that many complex things are all views on something that has an underlying simpler causal structure. So when we can find that the complexity is, it's not tameable, it's just that there is a commonality that you can refine and reflect. So translation is usually the way that we can find correspondences, and correspondences is the way that we can solve these harder problems of discovering that there are underlying similarities. So these are the hopeful things. That there's a lot of actually really not hopeful things too, but let's, you're asking about the hopeful things, so I'll stay there.
Yeah. Thank you, Paul. Let's give the opportunity now to Gemma to so give us her reaction to what we are saying here.
Thank you. So I'd like to start by commenting on Carlos's perspective on telescopes and so on, and encouraging everyone to read this very inspiring book by Richard Dawkins called The Extended Phenotype, which helps us see all these devices that surround us, such as glasses, artificial light, houses, cars, planes, and whatnot, as our extended phenotype, things that help our survival, very much as a spider web helps a spider survive, or a dam helps the river do the same thing. In this context, a computer is something that we build to compute, I think, at least like three orders of magnitude faster than our brain does. And it, of course, helps us explore and manipulate. So first, explore, understand. Way more is an understatement, by orders of magnitude more than what we mortal fallible beings coming from the savannah can do. And AI is kind of the latest development, fascinating, going in this direction. And perhaps within complexity science, one thing that I love and I'm particularly curious about is what we will learn about the brain, which altogether is ironic that we have been able to build such incredible things around us from some structures that, like our brains, that we do not yet quite understand. In fact, we are kind of, it is not the case that we build mobile phones because we are perfectly clear on how thoughts appear and how we do this thing called thinking and being conscious of ourselves. No, all these kind of fundamental notions about ourselves are not clear. So I am particularly curious about turning these tools, these AI tools, to the complexity of our brain. And I'm very excited to be living in this time when I hope that many of our secrets will be revealed.
Thank you. What if we now share ideas about what is the potential that these new technologies could have for the development of scientific knowledge, and particularly for enriching our knowledge in complexity science?
Well, that's a tricky question. I just mentioned that the models help us to reduce the dimensionality of the problem, but that's just extracting information from data. What about building new knowledge, finding out new knowledge? And what the recent models have been doing is really amazing. I mean, many people are going to tell you that large language models will only tell you what they learned. But it's not completely true. I mean, we train the models not only to tell to read what they learn, but to infer. And inference is something that gives you insights. Just a couple of years ago, people say that ChatGPT, for instance, was about the best PhD student that you could have, not to that level. No, some other achievements were, for instance, the ChatGPT, and that was I was talking, I think, about Model 4, could pass the exam that medicals have to take to be certified. No, that's something that very recently these models have been able to produce knowledge, and the way they have proven that is that they have submitted papers to relevant international conferences, reporting new discoveries, new findings. And the truth is that they were accepted. They were accepted. I mean, they really proved that they could give new insights. No, so what's the conclusion? I mean, how do we create knowledge? If you bring a philosopher, I know it's going to tell you something very profound. If you bring a priest, he'll tell you it's an act of God, something like that. No, but if you bring a computer scientist, it will tell you it's a skill that we develop through training during all our lives, right? So who tells or who can negate that? That's the way we create things. No, we learn things and we infer new things. No, so it's I think it's really happening. You know, computers are really helping, not only helping, but now then are discovering new things. So my very personal answer would be yes, they can help us to new knowledge. Yeah.
Okay, Carlos.
Yeah, I mean, of course, AI and other technologies will allow us to do many things that we have been unable to do, but I think we should also be a bit more modest and humble and be aware of the limitations. So one of the consequences of what Gemma mentioned in her talk is that if we want our machines, our systems to be reliable, let's say consistent, their creativity will be limited. And that's not a problem that we humans have, because we can arbitrarily change our, let's say, convictions or our axioms. And we don't want computers to do that, because then they wouldn't do what they were meant to do. So in that sense, they will always be limited, and they will not replace us in many aspects, unless we kind of become lazy and allow it to do so. But I think we should focus more on these limitations that the technology has. On the one hand, not to have overhyped expectations, but also on the other, to explore ways in which we can complement each other, because at the end, I don't think the tendency of computers is towards competing with humans, but more towards a symbiosis, and this is what we have been observing already for a long time.
Yeah, I'd like to follow up on that answer, because I think there's the potential for collaboration rather than competition sort of boils down to whether or not we're willing to change our current paradigm. I've got a couple of former students who have done a lot of meta-science work, and if you're not aware, over the last 30 years, innovation has declined massively within science and engineering. And it's really driven by funding agencies who identify right in front of your face problems that look like they are the high priority, and then that's the only thing that has money. So everyone has to work on these few things because of the money supply. Now, if we can get an AI system to automate completion of the thing in front of us, then we can spend a lot more time on a more interesting endeavor, which is, wouldn't you rather be an explorer with a map that has empty spots in it and say, I wonder what's in that empty spot? if we can get coverage automatically of the places where the only thing that's needed is a little bit of more effort to fill in the details, then that coverage reveals the gaps. Having the gaps revealed, those holes, provides us exactly with an old map that has holes in it, has blank spots. Having the blank spots, that's what we should prioritize for our research. That's what we should push as our knowledge frontier. And I do think that that's a worthwhile way of looking at the kind of collaboration that could emerge. Because if we can automate what we're currently doing, it will get done. And then the funding agencies will prefer something that's automated to do it rather than humans, because we're a lot more expensive still in their mind, although it's unclear whether or not the energy costs actually are going to make it cheaper. Anyway.
Thank you, Paul. Gemma, what about you?
You think that no one can really kind of see the future? What we can do is look at the past and try to learn from its lessons. And one constant lesson has been that no one was able to foresee all the novelties and the transformations of the world that new knowledge and technologies brought about, say, within the past 300 years in the various waves. So for this reason, I believe that AI can revolutionize many more things that we can imagine right now, and that the burden of proof, let's say, is on those that who defend that it won't revolutionize such many things. Like, if I don't see any fundamental obstacle to achieving those goals, then I tend to believe that solutions will eventually find its way. Now, that being said, what is of course very important is that we use AI responsibly, or that like the use that we make of this amazing tool is up to us. It shouldn't be left on its own. And again, we have an excellent historical example provided by quantum physics. Quantum physics has given us the transistors, the computers, lasers, amazing medical technology, now prototypes of quantum simulators, quantum computers, and so on. But also, it made the atomic bomb possible. So that's my kind of key example, which is a very recent one from the past 100 years. I'm not sure. I would also love to develop a symbiotic or cooperation kind of relation with AI, where it is at our service and for the good of humanity. But I'm not sure in what ways we should ensure that this is the case.
Thank you, Gemma. I'm going to take one idea that was discussed yesterday and connected with what you just said, Boris, and is the fact that when we wonder what are the limits of the capabilities of this artificial intelligence, we have to take into account that everything that he answers, or he or she or it answers to us, is built with the information it already has. But this, I think you're right. This doesn't mean that it cannot create new knowledge, because new knowledge can be, and is very common, that is built with previous things that were known already. And what about if we quickly give you opportunity to tell us, in your personal experience, what you have been, what you have found out these resources of large language models have been useful for you?
Well, from our personal experience, well, what we do is computer vision, and we have found interesting things. For instance, when we use generative models to construct, to simulate new images. But I have to say why we need to generate new images. We work with medical images, and often medical image databases are small. And in order to train other systems that help diagnose diseases, whatever you want, classify, etc., you need larger databases. So one way to get around with this problem is to create new images. New images that resemble, I don't know, some person with some X-ray with COVID or pneumonia or something like that. So we use these models, generative models, to create new images that have the typical lesions related to COVID pneumonia, and that's the way we enlarge the size of the databases that we can trade other synthetic data. Right, synthetic data. And there's a limit indeed. There's a limit because we have successfully created several images, but we found that you can create up to a certain number of images. Like I don't know, if you enlarge your database by more than 30%, the other system will not perform better. So there's a limit in which you can really use these systems to create new things. So general models are great because they generate new things, but that's our personal experience in our field.
Thank you. That's a good point. Carlos.
Yeah, so a few years ago, before the pandemic, with Gerardo Iñiguez, Carlos Pineda, Martin Sumaya, and more colleagues and students, we had a couple of projects with the Mexican Tax Authority, the SAT, and they gave us lots of data, 4 or 5 years of all transactions that were taxable, and also a short list of tax evaders they had identified, and we used AI and network science to give them a huge list of highly suspicious actors. And I mean, we don't know exactly who were they because data was anonymized and we didn't really want to know who was evading taxes. But let's say a few weeks in the newspapers, many businesses were kind of updating the taxes they forgot to pay for the last few years. So it was a successful project. More recently, Cynthia Rodriguez, she's about to defend on Friday her PhD. She used data from the university about student performance, and we were trying to predict after the students spend 1 year at the university, what were the chances that they would finish on time their careers or not. And I mean, there was certain success, but like the best, it was like 70% for different algorithms. And we understood that the problem is that there was overlap in the data sets in the sense that you will have statistics. Well, with the data we had identical students, and one would finish on time and another wouldn't. So we understood that in many cases, the nature of the data set will give you these overlaps, and that limits AI. So there will always be errors. And for this reason, we should be very careful on the applications we use AI for, because if we cannot tolerate errors, then we should measure the classifiability of the data sets we're training AI with. And if it's worse than the tolerance we have, then we should find another solution. And another limitation that we can see is that, of course, since we have so much data, it's tempting to include more and more data in our models. But the more variables we consider, the dimension of the state space explodes exponentially because each variable is a dimension. So even if we have lots of data, we very quickly end up with a situation where every point is unique, every state will never be repeated. So we won't be able to predict because we don't have, let's say, statistically significant data to train our models. So either we need to simplify our state space and then there will be errors, And on the other hand, we will never have enough data to be sure that there wouldn't be errors as well. So let's say these are just more limitations of AI that we should be aware of.
Yes, in my experience, we also have had this problem of overtraining, and then the neural network learns all the specific examples that you have given to them. Paul, please.
Yeah, my favorite use case for LLM, well, code assistance as a CS prof is trying to understand what my students are trying to do with their code. Code assignments are freaking awful to grade. And the ability now for Claude to interpret somebody's code, actually explain what it's intended to do, that's really impressed me. The flip side, larger code projects, still super bad. Small, like one-off routines, great as long as it conforms to what a lot of other things have done. Whenever I need to generate a set of things that would overcome what's called the accessibility bias. So we all have a major cognitive bias, and that's when we're making a decision, we'll always choose between the things that are easy to recall as options. What are the actual options? This is a great use for AI. Just stop. If you have a major decision, make sure that you have coverage over your options, right? So this is another great use. My current favorite use right now is I've got a student who has a really innovative idea for coming up with a much better Turing test. And it's essentially the fact that LLMs are creating such psychosis and such problems, the fact that they behave as if they are fully human, have intent, have wisdom from on high, act as spiritual gurus to people. Those sorts of things really delve into these issues of theory of mind and how humans would assess that something has intelligence, which is the Turing test. Turing test is not a great idea after we've seen LLMs. So what is the right idea? Anyway, I'll hold off on that because it would take a bit too long to explain. But I think this is a really interesting use right now of just from the human psychology point of view. LLMs are wickedly good at convincing us that there's more there at a human level than is definitely there. But that's on our side, it's not theirs, right?
Thank you, Paul. I think you brought a very good point. I hope we will have enough time to take it later once we complete the questions we have programmed. But I think that at the very end, if we increase the demands of the test, what we are asking is what is to be human? What is to be human? Because if we don't have a clear definition of that, we will not be able to put clear boundaries between ourselves and the machine.
So I'll just play off of this and say the key insight is that theory of mind is presumed to require ourselves to have a sense of our own mind, ability to predict and translate what we're doing into motives. And then I interpret other people's actions through that lens of what I would
consciousness.
do. And so we can prove that LLMs have no theory of their own mind. So they are not human in that respect.
Well, thank you. That's a great thing. Gemma, please.
Okay. So let me first answer the first question. Well, I just use AI as a personal assistant, mainly to help me understand theorems. It's quite helpful if there are details that I cannot find anywhere. It's like I say it as a promoted version of a search engine, like Google or whatnot. I don't know if it's making it up probably partly, or if it's finding this detailed explanation somewhere. But in that sense, it's very helpful. With regard to the mind and LLMs, that's precisely the area where I think they are most exciting. So maybe I'd like to take the question from a different angle than Paul, because questions such as how is the meaning of words stored in the brain? How do we retrieve it? How do we link it with grammar? How do we utter it? And then how do various mental disorders work? Were for many centuries somehow very difficult to investigate for ethical reasons, because we cannot harm someone on the basis of wanting to find out in what region of the brain this function is kind of operating, or we cannot deprive a child of its stimuli in order to investigate how they will grow up. And in this sense, I see LLMs as an external laboratory into our mind with similarities and differences. So I think it's extremely exciting. And in fact, questions such as how does reference in language work are ancient, where they were considered by Plato and Aristotle, can be found in introductions to metaphysics, the problem of universals, for example. And in this respect, so I believe that LLMs will give us new insights into these questions. And so I like to see them as experimental metaphysics, as helping us settle very old questions that were outside of our reach by providing this external lab. As I said, it's not like any human, but in some other sense, it has access to more information and more knowledge, if you like, than any human. So there are differences, but it's extremely valuable.
Thank you, Gemma. Yes, I agree with you. I think that we all knew each other. We knew ourselves when we know the others, and the way of knowing what we are. If I have black hair, I know it's black because I see others have, if I'm short or tall. So it's going to be very interesting to find out how this mind works. And this is going to bring an interesting piece of knowledge. Let's take a question that Chris proposed to us, and is whether artificial intelligence could be useful for the understanding of complex adaptive systems. Probably, Carlos, too, could be the more suitable for that now that you're presiding the Complex Systems Society.
I mean, we can use it in many different ways. I don't think it will kind of explain everything that needs to be explained because of the limitations that we already mentioned. But I think it's a tool that should be explored. So, yeah, I mean, maybe.
If someone else want to add to that, please.
The music just made me want to sing, but that's okay too. I think that there is a kind of paradox with studying adaptive systems. Currently, AI is trained on massive amounts of data, but usually that requires then implicit assumptions of data stationarity, and that's kind of, there's a tension then against being adaptive. So I think figuring out how to use this to study adaptive systems is a frontier, and but it's a really interesting question, because by addressing that question, it will actually advance and make more useful this tool, because this tool is going to be limited. It already is. If there are two modes in which LLMs now try to get data to you. One is to act as a search engine in which it focuses on the process of finding features that are good for retrieval of current data. So it's acting as a database retrieval engine. Another is to store in its network information itself, acting as a knowledge base. Right now, ChatGPT is mostly acting as a knowledge base. There are other engines that are acting more as retrieval, and you can tell immediately on the recency of the information that they give you back. It's a huge deal. So for an adaptive system, it's got to keep its data current, right? So this is a huge tension, but I'm basically telling this audience, this is a great problem to think about. So that's my take on it.
Thank you, Paul. Some of you also propose the question of whether we think that the large language models can understand language. And I think we are in a similar situation to where we were before, no? What is to understand? But what about Boris?
It all depends what understands mean. No? What do you think understanding meaning? A large language model learns language by training, right? So it learns like a child. No, child learn to speak by training, by listening to other people, and so they get. We all learn a functional way of language. No, so you ask me, I repeat, I answer a question. And that's a functional thing. That's a command function. But as we grow older and know more about things, we start thinking about language in other themes. For instance, the semantics, the semantics of the language, the cognition part of the language. And that's the kind of things that some people think that large language models cannot understand. For instance, if you it's like if you had an Asperger computer, right? So it's not able to understand sarcasm and things like those. So if you're having a conversation with a chatbot that tells you have a nice day, and you will tell him I'm not having a nice day because I had a big problem, etc., etc. So that kind of things is something that apparently computers can do. But I couldn't resist. I mean, I knew you were going to ask this, so I couldn't resist. And I did something that Gemma said that we couldn't do. I mean, asking a system to talk about itself. So I couldn't resist the temptation and ask ChatGPT, do you understand language? No, and you expect ChatGPT to tell you, yeah, of course, I'm a language model. So of course I understand language. Yeah, but surprisingly, you find the answer that it really tells you what the limitations are. And the limitations are in this context. I'm talking about now semantic and other kind of things. But I think if you take the simplistic point of view, how did we learn semantics? How did we learn cognition? How did we learn that we use all these concepts when we communicate with people? Again, it's by studying, by training, everything. So I think computers, large language models, will get to the point of understanding that kind of things. These are going so fast. The large language models that I wouldn't be surprised that they could dominate all kinds of language in a formal way.
With Jose Luis that is here, the other day we were writing a paper and we had the first draft, and we gave it to Gemini, and ask, well, build the abstract, build the discussion, and build the conclusions. And well, it really helped. And it did. You have the feeling that it understood what were the experiments, what were the objectives. So, Carlos, what do you think about it?
It reminds me of Searle's Chinese room problem. I think from 1980 or something like that. Well, most people here haven't been born yet, but there's this argument that there's an Englishman in a Chinese room, and he has some book with instructions on how to manipulate Chinese symbols, gets instructions under the door from Chinese scientists. He looks at the book and manipulates those symbols and produces an output which is correct, but the English person has no idea on what happened. So the argument of Searle is that machines are like that. They can give you the right response, but they don't really understand, which Chinese people do because then they read the language. But then we could apply the Chinese room argument to ourselves in the sense that we don't know how many things work and we still do them. And that, so, I mean, we don't understand how we understand. So what would be the Turing test for understanding? But being pragmatic, we can say that if computers do what we want them to do, then we can say they understand, and then we can say that their understanding is rather limited, because if we change context, then they're not so good at it. So that's a problem that all successful applications we see of AI are highly specific. So, okay, playing chess, playing Go, driving cars. But if you take a program that can manage a car successfully, cannot ride a motorcycle, less to cook or dance salsa or some other things. So let's say all the applications are very specific, and all the claims of artificial general intelligence they haven't delivered, and we managed to generalize. So maybe that's something that is missing in AI research. Whether we will get it or not in the next few decades remains to be seen. There might be that there's some inherent limitations. There might be something that will be a breakthrough, and then suddenly machines will be able to generalize, and then we will be able to say, oh, they understand in a very broad variety of contexts. But yeah, I think the question itself of whether they understand or not is contextual, because what Boris mentioned depends on what we mean by understanding, but also they will understand some things, but not others, depending on the context. And humans, we are broader at that, so then we can say, oh yeah, we understand it in a more general way.
Thank you, Carlos. Paul, when you ask this, I think it would be proper for you to consider also the fact that I think some people call it the embodiment issue. We have a body and we have physical experience, and this machine is learning, but without physical experience by the moment, because when it became a robotic, it could also have it. But what are your ideas on this topic?
Well, first, part of my talk that I'm about to give is really overlaps with this question quite considerably. So I'm going to avoid that part of it and then say it's absolutely the case that something's understanding of language would be limited, for instance, by not having a body. But in order to make the question more interesting, I want to make a distinction that we make even amongst ourselves, and that's how many people think that they have an implicit understanding of language versus an explicit. So implicit means you can use language. Explicit would be you could do all the grammar, right? How many people show of hands? Who's an explicit language expert? Yeah. So if an LLM has an understanding of language, it could emerge from the fact that there's so much human language in there, and we have a lot of this implicit structure built into it. It's remapping it and so on and so forth. And it's very good at these remapping problems. And so then the question is, what kind of representation would it have? does it have a human-like representation? And one of these interesting tidbits that came out recently is if you have one LLM generate random digit sequences, and then you train another LLM to just reproduce those random digit sequences, then the biases, all kinds of biases, racism, blah, 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 all kinds of biases get transferred from the first LLM to the second LLM just by learning the digit sequences it's producing. That means that the random seed that's going into the generative process is multiplexing or is embedding some information. Is that an LLM's secret language? There's been news stories to that exact effect, that they're speaking a secret language to each other. Yeah. Well, if that's their implicit language, it's definitely not explicitly understandable to us either. But I don't even know if that's an implicit language yet. Anyway, so this implicit-explicit distinction I think is really important, because a lot of times when the question is initially posed, we immediately assume that it would have an explicit understanding, like dereference the language appropriately and so on and so forth. The example that was just given here is you can use language. You can have an implicit understanding how language would be used for your own purposes, like get food from under the door when you're a prisoner, right? Even if you don't understand the language at all. What does that mean? Anyway, we'll pass it.
Thank you, Boris. Well, we will finish this session with your comments, Gemma, on this topic, because okay. Please.
Yeah. So I'd like to make several points. One is that I really don't know what understanding means. And I think that's a really important point, particularly because I've been quite busy with quantum physics, and I've been quite bold with the claim that I don't understand quantum physics. And I've been really trying to figure out what understanding means. So I'll say a bit more about that in a second. But for now, suffice it to say that, say, you read a poem, you read all these words, and these words evoke something to you which is fairly unique, has to do with your memories, your experiences, the current moment where you are, and you bind them together in this very intransferable way. What is going on? So maybe that's my starting point. I'm really confused, or I'm really unsure where to start understanding. And a further point that illustrates this aspect is that as I studied physics, and I believed I understood a bunch of things about the world, how it works, about the past, about the future, about the fact that the force causes an acceleration, about what physical objects are, and so on. And then recently, I've been reading a fair amount of metaphysics, and I realized I essentially don't understand any of the things that I took for granted. For example, I don't know how to define a cause. I don't know, I don't have an opinion on whether the past or the future exist or what to make of them. I don't know how to define a physical object. I don't know how to define personal identity, and so on and so forth. So I think this is intended to illustrate that often this notion of understanding relies on some so-called common sense notions, which are very difficult to put on solid grounds. And that brings me to the final point, which is that when you're asking this question, I believe that when you say that LLMs don't understand what they're saying, perhaps you mean that they don't have an ontology of the world. Like they cannot, if they say the sun is rising, they cannot relate that sentence to an experience, perhaps. we'd like to say a fact of something that happens with a star in our skies, in the skies of our Earth, of this planet where we happen to live. And I would just like to make a reflection here, which is that all our intuitions, all the things that we believe we understand by common sense about the world, essentially all of them are wrong. This is the lesson of physics over the past centuries. For example, it seems that the Earth is flat, yet it is not. It seems that the Earth is still, yet it is not. It seems that time passes in a uniform way. It does not. It seems that time is independent of the observer. It is not. It seems that time is continuous. Well, if we are to believe quantum physics, it should be granular. It seems that our bodies are created, yet they are not. So what I'm trying to illustrate is that language, natural language, reflects our intuitions and because I think ultimately it comes from us who evolved in the savannah and that helped us survive there. But these intuitions are largely wrong. In fact, they are so often wrong that it's really hard to know if we should trust any intuitions at all. So where does this leave me? It leaves me in the fact that I think the very word understanding may be a very misleading concept. Perhaps kind of suggested to us by natural language. So that's where I am.
Thank you, Gemma. Well, it's clear that what means understanding for some person is different of what it means for another person. And there is a say that says that 50% of all the things we think we know is false. And the problem is that we don't know what is the 50% right. Thank you very much.
Thank you.
Gracias, Gemma. Entonces, bueno, te escribo para seguir la conversación, ¿no? Pero te agradezco mucho. Y bueno, buenas noches ya, ¿no?